Welcome back to Differential Equations. This is part 2 of our lecture on undetermined coefficients. All right, so before you get started with this part, make sure you are comfortable with everything from part 1. Make sure for a given non-homogeneous ODE that you can identify the proper form for the particular solution that you would try, YP, and also make sure you have the steps that we outlined in part 1 in your notes. I told you to copy them down into your notes. If you didn't yet, go back to part 1, copy them into your notes, and then come back to now. All right, so if you're ready, let's jump into a third example here. This one is going to be it contains everything. It's a non-homogeneous ODE with initial conditions. I would say give yourself about 8 to 10 minutes for this. So give yourself 8 to 10 minutes, and we'll check in after that. Pause and work this one out. All right, welcome back. So let's go through the first few steps. All right, step 1, we're always going to look for the complementary solution. So we solve the homogeneous ODE where the right-hand side is 0. We get our characteristic equation. And for this example, the characteristic roots turn out to be complex. So here, our complex characteristic roots are -2 plus or minus I. So we're going to use the real part as -2 and the imaginary part as 1. All right, so it should be very straightforward to get your complementary solution there. With that, we can now go to step 2, looking for the particular solution. So we start by looking at the non-zero right-hand side, g of x, which is 35 times e to the -4x. And that's just a basic exponential function. So we're going to try for our particular solution an exponential function of the form a constant a times e to the -4x. All right, we're going to take yp, calculate its first and second derivatives, and then plug all that into the non-homogeneous ODE. The derivatives here are really simple to calculate. You just need the chain rule. Each derivative that you calculate introduces an extra factor of -4. And if you plug all this into the differential equation, you should be left with, after terms cancel, 5a times e to the -4x equals 35 times e to the -4x. Now, how we equate coefficients here is we're going to equate coefficients on both sides, where the like term is the exponential function e to the -4x. So if we do that, we get this simple equation, 5a equals 35, which we can easily solve to get a as 7. All right, so we get our particular solution, yp, as 7 times e to the -4x. We take yp, add that to yc, the complementary solution, and we get our general solution. Now, if there were no initial conditions in the given ODE, we would be done, but we do have initial conditions, which allow us to solve for C1 and C2. Now, before we do that, I want to point out, do not use the initial conditions only in the complementary solution above. We have to use the initial conditions in the full general solution, which is the complementary solution plus the particular solution. All right, so let's use the function initial condition. Y of 0 equals -3. The only thing you really need to know here are your values for sine and cosine of 0. which would be 0 and 1 respectively. So if you plug in x as 0, a lot of the terms simplify considerably. All right, so if you plug in x as 0, we get a very simple equation, which you can solve easily to get the value of C2 as -10. All right, now to find the value of C1, we're going to have to use the derivative initial condition. And this is where most of the work is, because given the general solution y, calculating its derivative is going to require use of product and chain rules. So if you haven't done that yet, pause now and give yourself maybe a minute to take our general solution y and calculate its derivative. We'll check in about a minute. All right, welcome back. So if you use the product and chain rules correctly, you should get a y prime that looks like this. We're combining the like terms, exponential sine terms, and then other like terms, exponential cosine terms. All right, also be careful with the last part of y, the general solution. The exponential function by itself, that's going to differentiate to -28 times e to the -4x. Now, once you got through all that work, which is basically Calc 1, calculating derivatives, now we can use the derivative initial condition, y prime of 0 equals 1. So plug in x as 0 again, sine of 0 is 0, cosine of 0 is 1, and we can use our value for C2. So plug that in, and you should get a simple equation here for C1, and you should find that it comes out to 9. And at this point, we are completely done. We have solved the non-homogeneous ODE with initial conditions. All right, now I would say, like you would, that this is a multi-step problem. So step 1, we find the complementary solution. Step 2, we choose the particular solution, plug it in, find the particular solution in terms of its undetermined coefficients. Then we get our general solution, and if we have initial conditions, then we go through some work to solve for C1 and C2. Now, as long as you are aware of the different steps or parts, each individual step should be manageable. It's just kind of keeping track of this all together that sometimes students tend to be overwhelmed. So make sure when you're going through homework questions, you kind of already know what's involved, the different steps, and then you leave it to the individual problems to go through the specific work. Before we get to example 4, I want to mention something about this multi-step problem. One of the topics we'll get to towards the end of our course, a topic called Laplace transforms. It's a way to solve differential equations, and instead of solving it in a multi-step problem like we did here, it basically solves a non-homogeneous ODE with initial conditions, kind of all in one big step. So we'll mention that again towards the end of our course when we get to Laplace transforms. All right, when you're ready, let's get to example 4. All right, now before you attempt this one is on the more complicated side, and it's complicated because some of the calculations get to be really cumbersome and long. So I'd like you to try this. Realistically, give yourself maybe 10 minutes to attempt this. So pause, give yourself about 10 minutes, and we'll check in after that. Realize, though, this one is a little more complicated. All right, welcome back. Let's go through some of the initial steps together. So the characteristic equation that's going to lead us to the complementary solution has a potential error in it. The correct characteristic equation is here, r squared plus 4 equals 0. A very common mistake that I find students fall into is just going from the ODE to the incorrect characteristic equation, r squared plus 4r equals 0. So just be careful of that. With this characteristic equation, the characteristic roots, the values for r, work out to plus or minus 2i. So thinking of that as a complex number, the real part is 0 and the imaginary part is 2. All right, so if you plug in those values of a and b, the exponential terms, e to the 0, just become 1. So we get sine and cosine solutions. That always happens when the characteristic roots are pure imaginary numbers, when there is no real part. All right, that should be straightforward, so we can move on to the particular solution. If we look at the non-zero right-hand side, g of x is 5x squared times e to the x. That's a degree 2 polynomial times an exponential. So we try a particular solution as a general degree 2 polynomial, ax squared plus bx plus c, but times e to the x. All right, I think that part is straightforward for students. Likely where you started to get stuck is in all the work that follows, taking yp and calculating its first and second derivatives. Now, it is straightforward. It only requires the product rule, but that's where some things can start to fall apart. Very easy to get lost. All right, so here I have the first and second derivatives. We basically use the product rule multiple times, and I'm not even going to attempt to try to combine like terms here. I'm just going to leave it as this big mess, as probably you did. All right, now what I want you to notice is there is only 3 types of terms present through that whole mess of yp, yp prime, and yp double prime. The 3 types of terms that are present are x squared times e to the x times e to the x, and just e to the x. All right, now one kind of more straightforward way to proceed is to take yp double prime and yp and plug them into the non-homogeneous ODE, and then just simplify, multiply out, and hope and pray that you kind of combine everything correctly. Now, what I want to do is kind of minimize some of that tedious work. I want to maybe step back and have you notice where these 3 types of terms occur in those expressions for yp and yp double prime. Worth pointing out, for this differential equation, it does not contain the first derivative term, so we don't need to worry about plugging in yp prime. All right, now before we advance to kind of extracting all these like terms to get the equation where we would equate coefficients, let's look first for all the coefficients of x squared e to the x terms. All right, so we're going to look at the differential equation on the left there, the non-homogeneous ODE, where we're plugging in yp and its derivatives. So looking at that differential equation, let's start with yp double prime. And we're going to look for all the x squared e to the x terms. The only x squared e to the x term is in the very last set of parentheses, ax squared in the parentheses, and then e to the x on the outside. So within yp double prime, the coefficient of your x squared e to the x term is a. All right? The next term in the differential equation is 4 times yp. So when we multiply yp by 4, your x squared e to the x coefficient would be 4a. So if we add the x squared e to the x coefficient from yp double prime to the x squared e to the x term from yp, or 4yp, we should get 5a for the coefficient of x squared e to the x. Now you can do that for the other terms, x times e to the x and e to the x. I'll leave that to you. That is a nice alternate way. Instead of plugging it all in and working it out by hand, we can just use the work that we have here, as long as you're comfortable with seeing these 3 like terms present throughout those expressions. All right, so if you did that correctly, we did the x squared e to the x coefficient. So we have in that non-homogeneous ODE 5a x squared e to the x. And if you extract your coefficients of x times e to the x, you should have 4a plus 5b. And if you extract all your e to the x coefficients, you should have 2a plus 2b plus 5c. All right. The non-zero right-hand side is 5x squared e to the x. Now we have our equation, the result of plugging in yp and its derivatives, and we can equate coefficients on both sides. And again, the things that we are equating coefficients of are these 3 like terms, x squared e to the x e to the x, and just e to the x. All right, now this is another checkpoint. Very easy to lose a single coefficient, and it throws your whole system of equations off. So before proceeding, make sure you are comfortable arriving at this system of equations. Make sure all your coefficients are accounted for. All right, now if you're okay with this system of equations, in other words, your work up to this point is all correct and good. If you got stuck, pause and make an attempt at solving for the values of a, b, and c. At this point, this differential equations problem just turns into an algebra problem. Give yourself about a minute. This system of equations actually solves very quickly. It again cascades. All right, welcome back. If you did that correctly, you should find a as 1. That's very easy to get from the first equation. Then once you have a, plug it into the second equation to get b. And once you have a and b, plug them both into the third equation to get c. All right, so that gives us our particular solution. And we just plug that back with the complementary solution to get our general solution. All right, again, this one was a little more complicated, but due to it being more, maybe more tedious, none of the steps I think were outright complicated individually. Calculating yp and its derivatives was just the product rule. Then it was a bunch of algebra combining and collecting like terms. There was a lot of it, but it was pretty straightforward. All right, make sure you're comfortable with this example. This is a good representative example of some of the ones that are on the longer side, the ones that take a little more time, but they are still solvable. All right, if you're ready, we're going to get to our last example. Now, if you paid attention in part 1, you might recall me saying something about what might happen with undetermined coefficients and what could go wrong with it. Well, let's go to example 5. All right, pause Give yourself maybe 5 minutes to attempt this, and we'll check in after that. Seems pretty straightforward, right? Let's check in 5 minutes. All right, welcome back. Now, most likely you didn't make a mistake with the particular solution. It's just, well, there's an exception we have to account for. And that's the purpose of this example. I wanted you to experience what could go wrong with undetermined coefficients before just outright telling you what that is and then how to fix it. So let's start first with step 1, finding the complementary solution. This one's very straightforward. You should get 2 distinct real characteristic roots, 1 and 4. So we get as our complementary solution c1 e to the x plus c2 e to the 4x. And it's worth mentioning, it wouldn't matter if you switched where e to the x and e to the 4x occur, just as long as you stick with that choice for your complementary solution. All right, that's straightforward. There's no problem there. We can proceed to step 2, finding the particular solution. So we take a look at the non-zero right-hand side, g of x, which is 8e to the x, an exponential function. So we try yp as an exponential function, a constant a times e to the x. Here, the derivatives are really nice. E to the x just differentiates to itself. So yp and its derivatives are all a times e to the x. That's pretty nice. All right, now let's plug in yp and its derivatives to the non-homogeneous ODE. And if you do that, what you actually find is the entire left side cancels out to 0. And we get this kind of nonsensical equation, 0 equals 8 times e to the x. So something went wrong. Ideally here, we should have an equation that allows us to solve for the value of a. And we don't here. There's no unknown a appearing in this equation, 0 equals 8 times e to the x. So what went wrong? Well, let's take a look at what our linearly independent solutions y1 and y2 are. Now, for our notation here, our y1 is e to the x and y2 is e to the 4x. Now just think about what happens when you plug y1 or y2 into the homogeneous ODE. Y and its derivatives would combine to give 0. Remember, your linearly independent solutions, y1 and y2, they come from solving the homogeneous ODE. So it should be no surprise that with y1 as e to the x, any function that's a constant times e to the x would have its function and derivatives combined to give 0. Well, that's exactly what's happening here. Notice your particular solution is the same thing. Yp is or contains e to the x, which is the same type of term as y1. And that's the problem. What we have to be careful of is making sure that our particular solution doesn't contain a term present in the complementary solution. All right, so what happened here is we actually made a wrong choice for the particular solution. It's not wrong from g of x, but we have to be careful to first look at our complementary solution. So if we take a look at the complementary solution, which contains e to the x, that is exactly our particular solution. So that would tell us if there's duplication between yp and yc, we need to make an amendment to our choice. We have to kind of do something to it. All right, and what we do, which I'll kind of state without proof, if you're going into physics or engineering, it just works. We'll save the proof for those of you maybe going into mathematics. But how we fix this is with this kind of important, I don't want to say theorem, but kind of fix for undetermined coefficients, which is as follows. If yp duplicates a term in yc, that was e to the x being duplicated in yp and yc, then we modify our choice of yp by multiplying it by a factor of x. So instead of using yp as a times e to the x, we multiply that by an extra factor of x, and we try instead a times x e to the x. All right, now understanding that undetermined coefficients, actually we have to be careful with choosing yp. We have to look at our complementary solution. With that out of the way, see if you can use this modified choice for yp to solve for the value of a. It should work out in this case. Give yourself maybe 2 minutes to see if you can solve for the value of a here. We'll check in about 2 minutes. All right, welcome back. If we go through the work for using this modified yp, there's a little bit of work using the product rule. That's very straightforward. And if you plug yp, the modified yp that is, and its derivatives into the non-homogeneous ODE, you should very easily find that a is -8/3. And there we go, we get our general solution. This example points out what could go wrong with a choice for the particular solution, and it also introduces how we fix that. Now there is a follow-up after this example, but just as a reminder, because I know before when I said this, you didn't copy the steps into your notes, so do this now. Copy this important remark into your notes, because the follow-up that we're going to look at references that. So pause the video right now and copy this into your notes. All right, now that you have done that, let's get to a follow-up. All right, and the follow-up here, I want to point out kind of the extreme case of when your choice for yp might need to be modified several times. All right, so we follow our steps. Step 1, we find the complementary solution. In this case, the characteristic equation gives a single repeated real root, r equals 3. All right. In this case of a repeated real root, your linearly independent solutions are e to the 3x and x e to the 3x. So no problem with getting the complementary solution. All right, we can go to step 2, looking for the particular solution. All right, now this is where I want you to pause. We begin the process of choosing YP by looking at the non-zero right-hand side, g of x. Now, the important remark, which you copied into your notes, tells you what to do. So pause and see if you can put the pieces together. What would be your choice for YP for this non-homogeneous ODE? Pause and write down your YP. Give yourself maybe 10, 15 seconds. All right, welcome back. Now, if you tried YP as A times e to the 3x, that's just your initial choice for YP based off of only g of x. Well, that is duplicated in YC. YP as A e to the 3x, well, that basically duplicates Y1. So this choice won't work like what we saw for the first part of example 5. All right, so you're a bright differential equation student. You copied that important remark into your notes, like I said. So you would think, oh, I just multiply this by x. Well, that is duplicated again. Multiplying your first choice of YP by x, we get A times x e to the 3x. Well, that now duplicates Y2. Any guesses how we fix this? Well, we just multiply by another factor of x. So YP as A e to the 3x, we actually have to modify that with 2 factors of x, giving us this proper or correct form for YP that will work. A times x squared e to the 3x. And we have 2 factors of x there included because there were 2 duplications of YP between Y1 and Y2. All right, now I'd like you to pause and go through, solve for this final choice of YP, A x squared e to the 3x. Give yourself maybe 2 minutes to see if you can solve for the value of A. We'll check in about 2 minutes. All right, welcome back. If you went through all of your work, which is a little complicated, requires product and chain rules, what you should find is that the value for A comes out to 1/2. And that leads us to our general solution to this non-homogeneous ODE. Make sure you can verify that you do get A as 1/2 and go through all the work necessary to get that. All right, that basically covers everything I wanted to for undetermined coefficients. Again, go back and make sure you understand everything in part 1 and part 2. This was our first of 2 methods to solve non-homogeneous ODEs.